Welcome to EDU World Space.
So to begin this problem, we must take a look at the gravitational force acting on the sphere. So we know that the gravitational force is equal to F equals mg, which is the mass of the object times its gravitational acceleration. So if we substitute the mass that we're given and 9.81 for the gravitational acceleration on Earth, we can compute the force. We can compute the gravitational force on the sphere. So if you do that, we're going to get 5 times 10 to the power -7 kgs times 9.81. So if you do that, we're going to get that the force of gravitational force, is equal to 4.9 times 10 to the -6 newtons. So now we must calculate the electrical force on the sphere, which can be calculated by this equation. So F is equal to the charge times the electric field strength. So the electric field strength of the sheet, since we don't know this one and it's not given to us, we must calculate it. So to calculate that, let's do that over here. So the electric field is equal to this over 2 times the permittivity of free space. So if we plug in the values that we're given, we can find out that this is equal to, since these numbers are all given, we know the surface charge density is given in the question, which is equal to 8 picocoulombs per meter squared. So if you do that, that's 8 pico is times 10 to the, so it's not letting me do that here. Let me do it over here. 8 times 10 to the -12. Since it's pico, I converted it back into coulombs per meter squared, over 2 times the permittivity of free space, which is 8.85 times 10 to the -12. So if you compute this, we're going to get that the electric field strength is equal to 0.4518 newtons per coulomb. Standard units, always good. So now if you go back into our electrical force equation over here on this side, we can now use the electrical field strength that we've calculated over here into this equation. So we know that the charge which is given to us is 3 microcoulombs, positive 3 microcoulombs, so it's 10 times -6, 3 times 10 to the power -6, times the electric field strength that we just calculated, which is 0.4518. So if you just put that into a calculator, we're going to get that. Hold on, let me just compute this one real quick, since I have not pre-done this. Let me just make the multiple sign there clear. So it's 3 times 10 to the -6 times 0.4518, which gives us a value of 1.355, or let's just do 15 times 10 to the -6 newtons. So we know that the net force is in a downward direction. So if you assume that y equals 0 at the sheet, so the gravitational potential at that point is equal to mg times y, or a height. So the potential energy at that point is U equals mg times an height, which I don't think we need to write down. So for the electric force, work done from moving from point A to B is this. So work done is equal to work done from the point A to B is equal to charge times the potential difference, A minus B. So that's the potential difference between the two between the 2 points. So if we isolate for the variable q to find the potential difference, we get that we can just divide both sides by q. So if you just do that, you can get rid of this q over here. And now we can solve for this potential difference, which is equal to, so now we can solve for the potential difference. So here, the Ka is its initial kinetic energy. Hold on, so at point A, to be at the sheet, and point B is at the distance y from the sheet. So if we take that, this potential difference is equal to the electrical field strength at y. So then the potential energy is UB is equal to negative EY EYQ. So now if we apply the conservation of energy law, which states that the initial potential energy UA plus the initial kinetic potential energy, the initial kinetic energy is equal to the final potential energy plus the final kinetic energy, assuming that this is taking place in ideal conditions and no energy is lost. So we know that the kinetic energy at the start is equal to 0 because it starts at rest. So there is no Ka in this scenario. So if we solve for Kb by moving the potential energy at point B to the other side, we can get that UA minus UB is equal to the kinetic energy at point B. So if we further expand on this expression, we're going to get that the potential energy at A, which we already discussed, was mg times in height. So the mg times y1 minus y2. So this is the starting height and this is the final height, minus, so the potential energy at UB is completely electrical, so minus EQ, and it's the same thing, so it's y1 minus y2 since it's the difference. So now we can just substitute, since we already know all the values for these, we can just substitute it straight into the calculator. So if you do that, or we can go a step further in simplifying this expression. So we can do that by factoring out the common expressions, which are y1 minus y2, since it's there in both. So if you just factor them out, we're going to get that mg minus EQ times y1 minus y2 is equal to the kinetic energy at point B. We need to find the kinetic energy to find the velocity, so let's keep going. So we know we're in the right direction. So now if you just substitute the values that we have for mg, which is 4.9 times 10 to the power, we calculated this before, so it's the first one, 4.9 times 10 to the power negative 6. So this is just the gravitational force that we calculated up here. Mg, negative, what is it? Negative 6, yep. Minus EQ, which we calculated right here. So it's 1.35 times 10 to the negative 6. Times the difference, which is just equal to 0.4 meters. This is straight from the question. So now if you put this into our calculator, we're going to get that. Hold on, let me just do this one real quick since I haven't pre-done this. So 1.35 times 10 to the negative 6. And all of this is multiplied by 0.4. If you do that, we're going to get that the kinetic energy at point B is equal to 1.42 times 10 to the negative 6. And you guessed it, it's of type unit joules. So now that we have the kinetic energy at point B, we can use the other formula for kinetic energy, which is 1/2 mv squared, and solve for the v in this case. So if you isolate all the variables for v, you're going to get an expression that looks something like this. So 2 times the kinetic energy over the mass, and just square root that whole thing since there's a square for the v, for the velocity in this top expression. So now since we know all these values, let's just plug them in. So 2 times 1.42 times 10 to the negative 6 over the mass, which is 5 times 10 to the negative 7. Hold on, let me just double check that real quick. Yep, the mass is 5 times 10 to the negative 7. And this whole thing is in a square root. So now if you compute this in our calculator, we're going to get the final answer for the velocity. So it's 2 times the kinetic energy, 1.42 times 10 to the negative 6 over 5 times 10 to the power of negative 7. Hold on, I did not write negative there, so negative 7. And this is equal to 2.07 meters per second squared. And that's it for this one. Thank you for listening.